Hi, everybody. I'm Philip. I work at Baseten. And yes, I am the author of Inference Engineering, which is the first sort of large scale guide to doing inference in production. But today, I'm not really here to talk so much about inference. I'm here to talk about products. And so let's get into it. When you send a picture of yourself, you should not do a group photo because then no one knows which one is you. So I'm going to let you guess which one of these people is me. I'm from Base 10. Base 10 is a inputs company. If you're in San Francisco, you've probably seen all of our pink and green buses all over. At Base 10, I have the privilege to work with a number of the best AI products teams in the world, companies who are taking the amazing capabilities of these large language models and other generative AI models and using them to deliver a very novel experience in a new form factor that wouldn't have been possible before. So today, what I'm going to talk about is a little bit of the history, the rise of open models, and why these AI native product companies are moving toward owning their own frontier models. We're going to talk about something called the trilemma, rather than the dilemma, because there's three things that we're trading on when it comes to building AI products. And we're going to talk about some of the inference engineering techniques that help you navigate that, as well as the sort of increase in the last few months of training specifically for inference and how new inference techniques are making these sort of overlap between inference and training bigger every day. So let's get into it. Get into open models. I never know whether or not I should include one of these slides anymore because sometimes it feels like everyone's on open models already. Obviously, GLM 5.2 was enormous news over the last week or so. And a lot of people have been trying that model out and having really excellent results. But open source has actually been here for a while. I've been with Base 10 since early 2022. And I remember I was working with open source models for embedding, for image and voice, the early Whisper model, for example. But they didn't really get a ton of prominence in the industry until the last 18 months or so with, the DeepSeek, the Llama family back in the day. Now we have new models from Quen and Kiely and GLM, of course, the AI. And then we also have folks like Nemotron out of NVIDIA, Gemma out of Google, training open models all around the world. And what's exciting about this is that not only are these models viable alternatives to the closed models for basically any AI workload, especially cost-sensitive and latency-sensitive, but they're now forming a foundation on which you can build these specialized models. So while the industry as a whole has been going through this transition, we also see, when I talk to hundreds of companies and what I see consistently is the exact same journey of, initial adoption through scaling, through integration of AI into their products. And it's throughout this journey that companies are really thinking about differentiation, which is the whole point of what I want to talk about today. 2 or 3 years ago, you could build a ChatGPT wrapper for anything and have people pretty excited to use it. Today, customer standards have gotten a lot higher very, very quickly. And so companies are thinking about, how do I move beyond just putting a language model in front of whatever service I was providing before, and start to think about extracting user signal from the things that they're building and refining that user signal into more and more specialized and specialized and effective intelligence at the specific tasks that the product is trying to solve. And you can think of this movement as almost like owning the frontier. We talk about a frontier model as a model that is at the efficient frontier of some combination of cost and intelligence, or latency or intelligence, or any combination of two factors that you want to talk about. And usually this label of frontier models is reserved for, your latest GPT model, your latest Opus model, and occasionally a handful of open models as well, your GLMs. your Kimi K2 back in the day, DeepSeek R1 before that. There's moments where the open source and closed source frontiers kind of meet. But what we're increasingly seeing is companies defining for themselves what frontier intelligence looks like, and then building the infrastructure and the processes required to own that frontier. So what we're finding is that the best products come from mixing closed, open, and custom models. Sometimes you just want the off-the-shelf intelligence of a GPT or an Opus. Sometimes you want the speed and efficiency of an open model. And sometimes you have enough conviction in the way that you're using AI in your product to invest in building something custom and delivering it to your users. So a great example of this is Harvey. We were fortunate to work with them recently on some legal agents orchestrating work. And they had been building on open models or on closed models for quite a while. And we're noticing kind of three problems with generic frontier models. The first was domain expertise, because these closed models are getting really good at a handful of tasks like coding, but they're not necessarily amazing at legal writing. Another issue is cost. As usage explodes, your token cost is going to scale linearly with that. And so with Harvey, they're obviously a fantastic company, a fantastic platform that's getting a ton of adoption. And with that comes a ton of cost. And then the final thing to think about is governance, is being able to, own every single aspect of the operation of the model, understand the traces, understand the reasoning that's happening, not just look at the outputs that you're getting. And so a long-term strategy for good governance requires end-to-end ownership of the infrastructure. And so what Harvey did with us is they post-trained a very small Quen model, actually. So starting with a small model is great because you're going to, out of the box, get incredible performance and cost characteristics. And by combining the training run with the actual harness and environment that they're going to be using the model with, they were able to get really fantastic results in terms of the intelligence of the model on their specific well-defined benchmark against some of the best models in the world at the time. And along with this, they were able to do something. Well, we're going to talk about this a little bit at the end. This is a preview of some of the training-aware inference-aware training techniques that we're using. They were able to implement a form of compaction to improve performance on long sequences of legal documents, as well as, of course, improve, latency and cost characteristics. So why does a company like this make that kind of investment? Like, what is driving them there? And the answer is that they're just trying to do the same thing that engineers have been trying to do for a long time. And that is trade-off between speed, cost, and quality. So you have, of course, speed, the latency of the system. This is incredibly important for the user experience, because this is going to be how the user perceives the service that you're offering. You have cost. As AI companies are scaling, obviously the most important thing is just growth. This is a brand new market. Everyone's well-funded. We all want to go win big chunks of the market. But at the same time, companies are getting to the size where you really have to think about costs. Token costs are very material, and you want to make sure that you're building a viable and sustainable business with strong unit economics. And then possibly the most important piece is this quality piece, where users want to have trust in the models that they're using, feel like they're getting access to the best intelligence in the world, and make sure that the outcomes that they're getting from the products they're using are really, really high quality. And the input serving piece is important for maintaining that. So each of these things is actually very challenging. A lot of times when we talk about inference optimization, we're just talking about speed. How do you overcome the fundamental limitations of the GPU compute, as well as the memory bandwidth and memory amount on these cards? But there's also challenges and levers for improvement elsewhere, like in cost, with trading off latency, throughput, and with quality, and making sure we're doing accurate serving and making sure that our techniques scale to serve larger and larger models. So let's take a look at inference engineering, and inference engineering specifically in the context of how each of these techniques relates to the cost, quality, and speed of the products that we're presenting. So what's exciting about inference engineering, the reason that you need, 256 pages to talk about this topic is because it's not just one thing. It's not just how do you get the LLM up and running on a GPU. It's not just, what do you know about PyTorch? It's not just one silver bullet performance optimization technique. It's a series of, performance and distributed systems problems sort of layered and composed together into a and there's a lot of pieces to the stack. Like there's the whole other for this problem, which is the infrastructure hack, which I'm not going to talk as much about here today. It's very, very interesting and has a lot of horizontal scaling problems. But my, solution to each of those problems is, just come use Baseten. And so it's a little bit, less interesting to hear that over and over again. What I am going to focus a little bit more on is some of the different trade-offs within the runtime and when each of these techniques is going to be appropriate for the performance profile that you're trying to hit based on your product. So the first place where, sort of product specific and highly differentiated inference engineering comes in is speculative decoding. We've had the idea of speculative decoding for a couple of years, and it started out as just a basic draft model. Let's say you have, Quen 0.5b and you have Quen 200b and they're running side by side. You use the small model to guess what the larger model might put out. And if those guesses are correct, well, then you've done it forward pass through a small model instead of a big model and saved yourself some time and resources. Speculative decoding is a really fun technique to start with because it's also a lossless technique. You're verifying every single intermediate output, which means you run no risk of quality reduction. But it is there's a lot of orchestration work around running those two models side by side. And it turns out small models off the shelf are not very good speculators. So recent speculative decoding work has focused a lot more on training specific speculators for a model. Two of the major techniques for that are Eagle-3 and DeFlash. And in each of these, you're asked to sort of train a speculator model based on the hidden states of the target model that is good at generating either a single or a sequence of draft tokens. And then, these models are usually a billion parameters, speculating against a model that's a billion parameters. So you do save a lot on inference time. Now, the thing is, when you are training a speculator, the question is, what do you train it on? Well, it turns out that speculator performance depends a lot on the actual nature of the input sequences and output sequences, not just the links to the patterns or whatever, but the actual time. So this is one of the early places where you can look at your actual product and come up with a differentiated inference when is saying, okay, I either have the ability to train on actual data that's passed into my product, or I have the ability to create a synthetic data set that very closely matches the type of information that my language model is processing. And I'm going to train speculator just for that. And when you do that, you generally see much, much higher token acceptance rates, which ultimately leads to improved tokens per second and improved overall system latency. Now, speculative decoding is mostly a latency thing. It is not so great with throughput because you are, adding that second model and the orchestration between those models to your system. So if your product cares mostly about quality and about speed, this is going to be a great optimization for you. If you're mostly concerned about cost and high throughput, it's going to be potentially less valuable in some cases. Now, a sort of optimization on the other half of the puzzle, speculative decoding is all about tokens per second. Kiely hash reuse is all about first token. Now, this is another place where the product decisions that you're making matter a lot, because in order for KB cache to be reused, the prefix has to be identical, not one token different. You can have a prefix that is 100,000 tokens long. And if 99,999 of those tokens are the same, but the first token in those sequences is different, you have a complete chaos. So you want to always move new tokens as far to the right, you input sequence as you can, to make sure that the sort of theoretical, the theoretical possibility of a cache hit is as high as possible. Now, actually delivering the cache hit, that is the input system's responsibility. That's the infrastructure's responsibility. And a lot of that in today's system comes down to routing as well as KB cache sharing. Because if you think about a system that's running at any reasonable amount of scale, you're going to have more than one replica of each model. And so the hard challenge is bringing each request to whichever replica is going to have the longest prefix match that can serve to skip prefill for all those tokens and massively accelerate your time to first token. This is going to help with everything. It helps with throughput, helps with latency, helps with cost. I mean, it doesn't really do anything quality, but certainly doesn't make it any worse. Now, speaking of quality, everyone's least favorite inference optimization, quantization, has the opportunity to improve both time to first token and tokens per second, making both prefill and decode faster by operating certain parts of each inference step at lower levels of numerical precision. Now, the thing to understand about quantization is it's not an all or nothing type of decision. You can quantize only the linear layers, only certain layers within model weights, or you can get more aggressive and quantize activations, KB cache, even attention if you're feeling real crazy. The thing with quantization is that LLM output, or really all generative AI output, is fairly non-deterministic. And so while you can kind of do intermediate rounding throughout the process of generating a token, you don't always know sort of which bit of rounding is going to be the one that blows off the flag. So in some cases, you see absolutely no impact. In some cases, you see quite a bit of impact. Usually where you see the most impact is due to two reasons. One, you have a distribution within the weights that has a very high dynamic range. So it has both very small values and very large values. And it's hard to encode that difference with lower precision. Or two, because you have relatively few weights and few parameters. And so there's very little information to calibrate against. We find that, with today's large language models, generally, especially weights only quantization, produces benchmark results that are, within the margin of error in either direction. Sometimes your quantized model performs better on a benchmark by half a point or whatever, and that just clearly is noise in the benchmarking system. But the way that we're able to be comfortable doing this is because of a data format called NVFP4, which addressed the first issue. So NVFP4 has dual scale factors. The scale factor is what you multiply the quantized value by to kind of get back to the original range. And by using two scale factors instead of one, at the expense of using slightly more memory, which the Blackwell architecture is designed to counteract, you are able to preserve quite a bit of dynamic range and generally keep really, really strong performance between that and having a very small block size. Each scale factor is only applied to a small number of values. You end up with a system that records basically the same information as the unquantized model, but just in a more efficient manner. And so again, this delivers wins across latency, throughput, cost, everything. You just have to be careful with your benchmarking and your calibration. Finally, parallelism is a place where you get to make some big decisions around latency versus throughput. Generally, most large language models today are going to be mixture of experts models. There are a handful of dense models out there that reach the size we want to parallelize, but for the most part, it's going to be mixture of experts models. For these models, you have the choice between a couple different types of parallelism. There's tensor parallelism and expert parallelism, including something called wide expert parallelism, which is just EP across your, NBL 72 instead of across the standard index node. And the thing to keep in mind is that with different parallelism strategies, you can either improve latency or throughput and thus cost. We generally find that for most workloads, tensor parallelism is going to be somewhat more of a latency optimization, and expert parallelism is going to be somewhat more of a throughput optimization. But as you kind of profile a given workload, you can test against multiple different configurations and see which blend of it gets you to the point along that efficient frontier that you're looking to hit. And then a newer optimization, something that we've been rolling out in recent weeks and seeing really great results with, is disaggregation. So disaggregation is the idea that, okay, we have prefill, that time first token, we have decode, the tokens per second afterwards. These are very different workloads with different constraints. There's going to be different optimizations that help one or the other. And so why don't we just put these two things on separate nodes, separate sets of GPUs, and just share the KV cache between the two? Now, obviously, this creates a bunch of orchestration issues. We use NVIDIA Dynamo as the toolkit to protect against this. But if what you get out of it is you get quite a bit of efficiency on both prefill and decode, especially on prefill. You get some big steps up there. And we found, for example, on GLM 5.2 that in our system, we got about a 2x improvement on tokens per second in decode through disaggregating the inference. So this is a really promising technique. The trade-off here is scale, mostly. Like, you get better performance, you get better overall system throughput, but you need to be running at a scale where not only one node of it makes sense, but having, 3 to 5 nodes that you can do, multiple prefill logos per decode logo and operate at that kind of scale. That's what allows you to kind of get these excellent results in production. Now, these are all kind of the standard inference techniques that I've been talking about for a year or more at this point. But what's kind of new and exciting in the field of inference engineering today is training for inference. So we have these two factors coming together. One is that more and more companies are tuning models, they're training custom models, they're investing in the process, creating the model that they want to use. And on the other side, they're getting really good at inference. They're understanding these inference engineering techniques and understanding the impact that inference has on the product. So when these two come together, you get the idea of, well, if we're training a model anyway, and if we know we're going to have to do inference optimization anyway, how can we do something in the training process to make that inference a little bit easier? So, in the sort of traditional in the book, for example, inference engineering assumes that the weights are fine. But that isn't the whole story. A lot of recent optimizations come from training. So spending some time in compute upfront on training can yield big savings on inference. And I'm going to give you a quick overview of some of the optimizations that we've seen for that. So a big one is quantization-aware training. Again, we talked about with quantization that you have the ability to, just directly do post-training quantization of weights into these high precision, highly specific floating point data formats that preserve quite a bit of accuracy. But if you're still seeing loss from that compression process, quantization-aware training allows you to train into that precision natively rather than running the quantization afterwards. And if you do that, which we're increasingly seeing open models come out with quantization-aware training to certain precisions, you eliminate the chance of quality loss from that quantization work while still gaining the benefits of the smaller data format. There's also, like we spoke about with Harvey KD compaction, we just published, the post-training team at Baseten published a new paper about STIL, which is a method trained with on-policy data to retain KV information through compaction steps. Obviously, like we discussed with KV-aware routing, the KV cache is very valuable. And if you're able to keep your input sequences the same from step to step, you're able to see a lot of savings on prefill. But holding KV cache is expensive. sharing is expensive, routing is expensive, and sequences can get very long. And occasionally you might even run against the context window limits of the model itself and need to compact the information, which voids the KV cache because you've changed the token order slightly. Doing KV compaction at the model level and doing it in training so that you're able to teach the model how to do this compaction and how to retain information provides some relief against some of these KV cache challenges during inference. And finally, DeFlash. We mentioned this during the speculative decoding slide. So DeFlash and Eagle-3 are the newest speculation methods. DeFlash is a bit newer, and it's overall a higher performing method. So like with Eagle-3, you still need to train a DeFlash speculator, and you actually train it to generate an entire sequence in a forward pass from hidden states, rather than individual tokens like Eagle-3. So you remove the sort of auto regression bottleneck out of your speculation. So lots more to come, I think, in these training-based inference optimizations. Again, if you're training a model anyway for quality reasons, you probably also want to train in the speed optimizations, the latency optimizations, the throughput and cost optimizations that you're ultimately going to need to do at the inference step anyway. So there's a lot of work that you can do up front by understanding what inference is going to look like in order to set yourself up for success after the training is complete. So thank you for having me in Infer Summit, folks, and thanks everyone for listening to. If you'd like to find out more about inference, you can connect on Twitter and LinkedIn, where I'm publishing our inference work as often as I can. And then you can also read Inference Engineering. This is the book that I published about 4 months ago. It's a very good introduction to the field in general, and it is free at this QR code at baseten.com/inference engineering. And these paper copies are also available for purchase in more than 20 countries. So thank you so much for your time today. And that's inference for product differentiation.
Thank you, Philip. That was a lot of good stuff there about optimizations, techniques. And this is one of the reasons why the inference area is very fascinating to me. But at the same time, it can be a little bit overwhelming because of all these options that we have, right? There's a great question that I'm going to bring up, and maybe you can take and answer this.
Yeah, so this is kind of the holy grail of inference optimization, right?
Mm-hmm.
In the past, we thought about inference optimization very statically. It's like you come up with the appropriate configuration and then you run it. And the world that we're moving toward is one where rather than automatically deciding up front what optimizations you use, you just run the system against traffic, observe what is happening, and adjust your optimizations. Today, that's still at least semi-manual process of, picking a configuration that you think looks pretty good, deploying it, getting feedback, and then iterating. But a sort of ultimate self-improving input system would sort of automatically A/B test different configurations and iterate and sort of help climb toward the optimal serving method.
Got it. Okay. Yeah, so thank you for sharing your book, and attendees, if you are interested in this area, definitely grab a free copy of this from Philip. Another great question that we're going to bring up here about what would your recommendation for a book that shaped your thinking as an AI engineer?
That's a great question. I think that I recommend a bunch of great resources in Appendix B. I think that one that does a good job of diving a lot deeper into some of the technical aspects of this optimization work is Chris Begley's new book. And then, yeah, a lot of what I've learned has come more from blogs, more from just like on the job learning versus out of books. I feel like the space is so new that there's not a lot. Most of the books back here are straight plus books or science fiction. But I like to read very broadly.
Definitely. Continuous learning is a part of the job, and because this field is exciting as well as evolving at a pretty high velocity. Cool. Philip, again, thank you very much for spending time with us.
Thank you
We're
for
going to move on